Well, thank you very much for the invitation. It's a pleasure to be here. It's my first time in Russia as an adult. So I was here once as a teenager, it was some time ago. So it's nice to be back. So the topic of this lecture will be stochastic partial differential equations. And in particular, I want to talk about the class of rather singular stochastic partial differential equations. But before I come to that, so maybe I should start with introducing somehow the simplest, sort of like the simplest prototype of the kind of equations that we're going to be interested in. And that's going to be a stochastic version of the heat equation. Okay, so you all know the heat equation. So the heat equation is just dTu equal Laplacian u. And well, there's a natural stochastic perturbation of the heat equation. So which I'm going to write in this way. And so in these lectures, whenever I write a psi, psi will always denote space-time white noise. So space-time white noise. And so what do I mean by this? So space-time white noise, well, in one dimension, white noise is formally just the distributional derivative of Brownian motion. Okay? Or another way of saying it is, so white noise, well, in acoustic, also white noise is a noise where every frequency comes in at about the same intensity. Okay, so if you took the Fourier transform of this, then the spectrum would essentially be flat. Okay. But a formal way of describing this is to say that this is a generalized Gaussian random field. So it's a random distribution, so I cannot evaluate it at points. Okay, so I cannot just give you a correlation function in the sense of the correlation between 2 points, because I can't evaluate at points. The only thing I can do is test it against test functions. Okay? And so a Gaussian random distribution is one where if you take any collection of test functions and you test it against it, well, then you get a Gaussian random variable with as many components as you have test functions. Okay? And of course, Gaussian random variables are completely determined by their covariances, so I just need to tell you what the covariance of this is. So I take 2 test functions, say phi and psi, that go from, so this is on space-time, and my space here, I'm always going to write d for the dimension of space. So space-time is going to have dimension d plus 1. Okay. And so these are test functions in space-time from rd plus 1 to r, so smooth, compactly supported, as nice as you want. And then if I test psi against these 2 test functions, and I take the expectation, then I just get the L2 inner product between phi and psi. Okay, so that's the definition of white noise. And you can easily convince yourself that formally what this means is that, you know, if you had the right to evaluate this at a point, and then you wanted to write down the correlation function, then the correlation function would just be a delta function, okay, which is of course not a function, so you're not really allowed to evaluate that point. Okay, so that's the simplest example of a stochastic PD. And so let me just show you a more concrete example of a sort of discrete model maybe where this equation arises, say in one dimension. So in one dimension, this is really some sort of a natural evolution on Brownian motion. So what do I mean by this? Well, take the following discrete model. So you take a function that only takes value that goes from integers to integers and is only ever allowed to change by plus or minus 1. Okay, so basically a random walk, but you start with an arbitrary realization. So you have a function like this, so it's allowed to go down, or it's allowed to go up. So take a function like this from z to z. And now you can put a very natural evolution on these functions, which is the following. You say, well, at every point here, I have a Poisson clock. They're all independent. And so whenever one of the clock rings, so say that one rings, then you look at that location. And if you see a local minimum, you just flip it. You turn it into a local maximum. So say here, I turn this into this. It kind of goes up. Or say if it was this one that rings, then you have a local maximum here. You go the other way around. You turn it into a local minimum. And if, for example, this one rings, well, then you do nothing because you have neither local maximum nor local minimum, so there's nothing you can do. Okay, so this is a very natural evolution on these curves, right? And well, if you want to build a scaling limit of this, so you look at what happens if you scale everything by epsilon, and you scale it vertically by square root of epsilon. And then it turns out that the correct way of scaling time here is you have to scale it by, okay, so it's going to be probably a fourth root of epsilon or something. And then what you actually see, no, it's actually square root of epsilon as well. It's epsilon square, sorry. Epsilon, you scale time by epsilon square, you scale space by epsilon, you scale the heights by square root of epsilon. Okay, so that's the correct scaling in which you get a limit. And the limit that you get here is exactly this stochastic heat equation. Okay? So that's one way in which it shows up, but it also shows up in more sophisticated models. So for example, if you take, so that's something which to the best of my knowledge is not really proven, but it's kind of clear that it should be the case. Which is if you take a 2D easing model on a large box, and you take boundary conditions, say that are pluses on one side of the box, and minuses on the other side of the box, and you start with an initial condition that, well, say you have an initial condition that has all minuses here and all pluses here on every grid point. And now you take a temperature which is below the critical temperature, and you put Glauber dynamic on this. Then the interface, there's an interface here that separates pluses from minuses, which at the beginning is just completely flat. And then if you throw Glauber dynamics on the easing model and you look at what this interface does, if you're below the critical temperature, there's the natural conjecture is that you also converge to the heat equation. So at least it's known for the Gibbs measure that if you take the Gibbs measure below the critical temperature and you scale this correctly, you see a Brownian bridge here, and the Brownian bridge would just be the invariant measure for the stochastic heat equation. Okay, so now the kind of equations that we're going to look at are going to be basically nonlinear perturbations to this stochastic heat equation. Okay, so let me give you a few examples. So nonlinear perturbations. And so they are perturbations not in the, so they are not perturbations in the sense that they are small, that they differ by a small amount from the heat equation. They differ by order 1, but they are still perturbations in the sense that if you look at what happens very, very locally, if you zoom in very locally into the solutions, then they will look very similar to the stochastic heat equation. So in that sense, very locally, there will be perturbations. Of course, globally, they won't. Okay, so the first example, so in one dimension, the first example is the KPZ equation. And so that's due to, so KPZ is Kardar, Parisi, and Jan. So there might be another KPZ showing up in other talks, which is a different KPZ. So here, you start from the one-dimensional stochastic heat equation, and you add a nonlinearity of the type square of the gradient of the solution. And so here H, well, so one way, for example, to obtain this KPZ equation, so that was done by Bertini and Giacomin in the late 90s, would be to take exactly this model here, okay? But this time you make it slightly asymmetric. So instead of saying when the clock rings, well, you flip it up or you flip it down, so you just do whichever flip you're allowed to do, you say that, well, the upwards flip happens slightly faster than the downward flips. Okay, so you make the thing slightly asymmetric, so it flips up at slightly higher rate than it flips down. So then on average, the whole thing is actually going to move up. And so what you do, you have to recenter it so that it stays more or less still. And then if you take the correct scaling limit, in a regime where the asymmetry between the upward and the downward flip goes to 0, but you scale out at sufficiently large scale, and if you choose these scales correctly, then you can get precisely this KPZ equation. And we'll see also a bit later that these equations, they have some sort of universal character also, in the sense that, as we saw in Jean-François's talk, so in the sense that you can find a whole bunch of models of interface fluctuations that if you rescale them correctly, then they converge to a solution to this equation. Now, one thing which is important is that here, this equation here has a certain scale invariance. Okay, so you can kind of convince yourself that if you do a rescaling, which depends on the dimension, you get exactly the same equation back. This equation here is not scale invariant. So there's no way of scaling this equation so that you get exactly the same equation back. There are somehow just too many terms on the right-hand side that scale a bit differently. And so you will never get it as a scaling limit for a fixed model, right? So since by definition, basically scaling limits have to be scale invariant, since this is not scale invariant, you cannot obtain it as a scaling limit. So the only way that you can obtain it is by tuning a parameter, by having a family of models with a parameter, and to tune the parameter at the same time as you scale out. Right? So here the parameter would be the asymmetry between the rate at which you flip up and the rate at which you flip down, and you have to send this asymmetry to 0 at the same time as you scale out if you want to obtain this. Okay, but in that sense, then it does have a certain universality in the sense that there are many classes of models where you have a parameter that you can tune, where you still get the same limit. Okay, so another example is the phi-4 model. So here it's, this equation really just makes sense in dimension 1. So the phi-4 model is this model here. So this makes sense in dimension strictly less than 4. And this one, you get it, at least formally, and you can actually prove it in dimension 2, 1 and 2, you can prove this. You can obtain this as, for example, if you take an Ising model again, but this time which is almost mean field. So instead of taking nearest neighbor interactions, you take interactions with a very large number of neighbors, and then you let the range of the interaction go to infinity, but simultaneously you rescale the model, and the scale at which you rescale it is somehow even larger, okay, than the scale of the interaction, so that at the scale at which you look, the size of the interaction goes to 0, but at the microscopic scale, it actually goes to infinity. Okay, so if you look at that kind of regime, and you tune the temperature so you're close to the critical temperature, then you obtain this model here. And that was proven by Murat and Weber recently in dimension 2. And it's somewhat clear that the proof would also work in dimension 3, but it's technically a nightmare, so nobody has done it.
Why do you say that D is less than 4?
Because in dimension 4, then the equation does not make sense anymore, and you expect to have only essentially Gaussian processes, to not have any non-Gaussian object. And actually, in the case of easing, also you only expect to. It was basically proven that you just get the free field in the limit. You don't get a non-trivial limit.
But starting from which dimension, the say definition of notion of solution here becomes not trivial?
Dimension 2. Right.
So dimension 1 it is.
So in dimension 1, this equation makes perfect sense. The solution is a function, and there's absolutely no problem. And as we'll see in dimension 2, already the solution will become a distribution, and then it's not clear what the equation means. And so in dimension 2 and 3, you have to work in order to give a meaning to the equation. And then in dimension 4, somehow all hell breaks loose and the whole thing breaks down. And that's somehow a relatively general fact, right? So typically these things in somehow low dimension, they tend to make sense without any problem. And then when you increase the dimension, at some point you start to have difficulties giving a meaning to the equation. And then at some point things break down altogether. So there's another example is a sort of continuous version of the parabolic Anderson model. So the parabolic Anderson model, you think of it, think of a particle, say, performing a random walk, and it evolves in a random environment, but the environment doesn't affect the motion of the particle, but it kills the particle. Okay, so you have a potential, if you want, a random potential, and where the potential is high, the particle has a high probability of being killed, and where the potential is low, it has a low probability of being killed. Okay, and so you take a random walk in a random environment like this, and now you condition it on surviving for a long time, for example. And then if you look at the probability distribution, the survival probability distribution, in the limit, so again, it's not a scale invariant object, so again you have to have a small parameter, and so here the small parameter would be the strength of the potential, so it's somehow the rate at which you kill things. So you say you kill the particle at a relatively small rate, so that if you want, there's a separation of scale, so that it typically goes quite far before it gets killed. Okay, so that the distance that it covers before it typically gets killed should be relatively large. Okay, and then you take a limit where this distance goes to infinity, but then you also scale it out. So you see something non-trivial. And what you see here then is a heat equation with term u times eta. And so here, well, okay, so I write eta instead of xi because what you get here in the limit is just white noise, not space-time white noise. Okay, so it's the same as space-time white noise, but this time instead of the covariance formally being a delta function in space-time, it's just a delta function in space, and it's constant in time. Okay, and so that, if you want, that represents somehow the scaling limit of the environment, which in the limit just, if it decorrelates relatively fast, as you rescale it, it just converges to white noise. But the environment here is static, and it doesn't evolve in time. Okay. And there's a last example which I wanted to write down, So let me write it as G SHE. So that would be somehow a geometric stochastic heat equation. So that would be the question of what is the natural. So this was a sort of very natural evolution of continuous curves, right? So the scaling limit of this is a very natural evolution on continuous functions from R to R. You can ask yourself, what is the natural random evolution on functions, say, from the circle into a manifold? Okay, so if you give yourself you fix a manifold, and now you take a continuous function from the circle with values in the manifold. So it's basically just a, something like this. And now you ask yourself, what's the natural random evolution for these kind of curves? Okay? And well, so you know, you would think of something which is sort of the analog of this. All right, so the analog of this, for example, one thing you could do is you could discretize your curve. All right, so now you have a, so say you have a piece of your manifold here, and now you have a piece of curve, and you think of it as being little beads connected with somehow little springs. And on the one hand, there is an effect here that tries to make these things line up, right? So there would be so you would put a force that sort of makes them line up. So they try to form geodesics on your manifold. But then on the other hand, each of them would sort of independently, you would just independently put a noise on each of them that kind of keeps them moving. And the natural structure for the noise here would be simply the thing, so that in absence of interactions with the neighbors, they would just perform Brownian motion on the manifold. Right? So Brownian motion on the manifold is clear. It's just the Markov process that has the Laplace-Beltrami operator as its generator. And so you take simply independent Brownian motions. Well, you start from independent Brownian motions on the manifold, but then you make them interact in such a way that they want to line up to form geodesics. Okay, so that would be a very natural evolution for these beads. And then now you want to take a limit where this becomes a continuous function. And the distance between these beads goes to 0. And if you just formally write down what you're supposed to get, then what you obtain is something like this. So it looks a little bit like this KPZ equation. So you have, so now you have coordinates. So say you put yourself in a coordinate chart. And so now h is also the position. So you parameterize your curve. You have an x. So x would be now the parameter along the curve. So that's my space variable. Okay, and the time variable is the time in the evolution. And so again, it's described by a function of x and t. But now it's a function with values in the manifold, so it has still coordinates. So you put a coordinate system on your manifold. And so now the alpha refers to the coordinate system in the manifold. Okay, and so the evolution of this would be given by, same as before, but now there would be a nonlinear term which is given by the Christoffel symbols of your manifold. And then there's a noise, and the noise naturally should be somehow, again, white noise, but this time locally it should have a covariance which is given by the metric of the manifold. And one way of doing this is to just take a collection of vector fields which generates the metric. So say sigma I alpha h, psi I, where the sigma i's generate the metric in the sense that sigma I alpha, sigma I beta, sum over I is the inverse metric tensor. Okay, so this would locally, at least intuitively, it would give you locally something Gaussian with covariance given by sigma I transpose, which is then just a metric tensor. Okay, so this would be, if you want, the noise part, and this part is the part that tries to make these things align in order to become geodesic. Okay, so these here are the Christoffel symbols. Okay, and so I would maybe encourage you to actually check. So it's a lengthy calculation, but it's something one can check, is that this is actually invariant under coordinate transformations. Right? So it's, if you just write down the heat equation, then it's not invariant under coordinate transformations. And then if you just look up, how do the Christoffel symbols behave under changes of coordinate charts? Well, they behave exactly in such a way that this equation here is invariant under changes of coordinate charts. Yeah. Okay, so that's the kind of equations that we're going to be interested in. But so before we go to these nonlinear equations, so let me spend a little bit, go back to the stochastic heat equation and spend a little bit time on just trying to figure out how the stochastic heat equation behaves. And so the first question is that of the local behavior. So how rough are the solutions to the stochastic heat equation? Okay, so in one dimension we already kind of know, right? Because we've seen that, or at least I told you, that this model here rescales to the stochastic heat equation. And it's somehow reasonable to assume that if you run a dynamic like this for long enough, this is essentially going to look like a random walk after a while. And of course, the random walk rescales to Brownian motion. And Brownian motion, we know exactly how it looks like locally. And so you would expect the solution to the stochastic heat equation in dimension 1 to locally look like Brownian motion. Okay, and that's true, of course. But then this doesn't actually tell you how it looks as a function of time. Okay, it tells you that at fixed time, as a function of space, so the function of this variable here, it should look like a Brownian motion, so it should be Hölder half. But it doesn't tell you how it should look like as a function of time for a fixed point in space, for example. Okay? So in order to do this, the first thing I want to do is give you a, maybe I should do it like that. Give you maybe a slightly strange definition of the usual Hölder spaces. Of course, you all know how you define Hölder spaces. But so, okay, so first on RD plus 1, I claim the natural way when you look at parabolic equations like this, the natural way of measuring distances in RD plus 1 is not by taking the Euclidean distance, but it's by taking what the so-called parabolic distance. So let me just introduce parabolic distance. So if I take a point in RD plus 1, okay, so I'm always going to write, well, t for time coordinate, x for space coordinate, and a space-time point, I'm going to typically write it as z. So z is not a complex number, it's an element in RD plus 1. And then the norm, if you want, of such a space-time point, but you have to be a little bit careful because this norm is not homogeneous in the usual sense. By definition is the usual norm of x plus the square root of the absolute value of t. Okay? And so, you see, so this norm has the property that it's homogeneous under the scaling, tx goes to lambda square t lambda x. Right? So if you do a transformation like this, then under this transformation, this norm gets multiplied by lambda. And so this norm is very natural when you analyze these kind of PDEs, because the heat equation is precisely invariant under this kind of scaling. Okay, so this is the natural scaling of space-time. And so this is the natural norm that you would want to put on space-time. So one thing to note is that with this norm, if you take this distance, so of course this gives you a distance function as just the norm of the difference between 2 points. And under this distance function, Rd plus 1 has actually Hausdorff dimension d plus 2. Okay, and that's because of the square root here. Okay, and so in some sense, you should always think here of Rd plus 1 as having dimension d plus 2. Okay, so the time direction, in a way, kind of counts double because of this square root here. Okay. And okay, and so now, oh yeah, and so one other thing is, if you have a function, for example, now which is a alpha Hilda, so say you have a function f from Rd plus 1 to R, which belongs to C alpha, say for alpha between 0 and 1, the usual C alpha. But now when I say that such a function is in C alpha, it means C alpha with respect to this distance function here, right? Now that means that in the time direction, it's really C alpha over 2 in the usual sense, right? Because what does it mean if you look at f of, say, tx minus f of sx, well, it's bounded by this distance here, so t minus s, well, x minus x, which is 0, to the power alpha, right? But this distance to the power alpha is t minus s to the 1/2 to the power alpha. Okay, and so in the usual sense, it is really Hilda alpha over 2, even if I use the notation C alpha. Okay, so C alpha really means C alpha in space and C alpha over 2 in time, because we use this funny kind of metric. Okay. So now I claim that there's a natural definition of C alpha which might look a little bit strange, but which has the advantage that it generalizes very easily to arbitrary values of alpha, even to negative values of alpha. Okay, and that's the following. So if you take a test function phi from Rd plus 1 to R, I'm going to write phi z lambda as the test function, say, of z prime, as the test function given by phi of z prime minus z, in a way divided by lambda. But you should, when I write divided by lambda here, really means that the x coordinate is divided by lambda and the t coordinate is divided by lambda square. Okay, and I just don't want to write it separately. So you just recenter it, you rescale things by lambda, and you put out a factor lambda to the minus d minus 2. Okay, so now I've scaled it like a delta function. Okay, so this is really just a way of, you take your test function phi, you recenter it so that it's centered around the point z, the space-time point z, and then you squash it horizontally. So if phi is a bump of size 1, you squash the bump horizontally so that it becomes of size lambda, and it's lambda in this sense, so in the time direction it becomes of size lambda square. Okay. And vertically you stretch it in the correct way so that the integral remains 1, okay, or remains the same as that of phi. Okay. And so let me write, I don't know, Well, okay. And so now I can say that a distribution, say zeta, is in C alpha if and only if, when you take zeta and you test it against such an approximate delta function, basically, but then what you get is of order lambda to the power alpha, but you have to start with a test function which kills polynomials. Okay, so you take a phi, which is not an arbitrary test function, you take a phi which is such that the integral of phi, say phi of z, p of z dz is equal to 0 for any polynomial p which has degree less than alpha. Okay, and then the degree here should also be counted in the parabolic sense, so that the time variable has degree 2 and the space variables have degree 1. So you take any function any test function which kills polynomials up to the degree alpha, you test your distribution against such a test function, and you want that the result is of order lambda to the power alpha, where this here is somehow locally uniformly in Z, uniformly in lambda, say between 0 and 1, and uniformly in phi with, say, supported on the ball and sufficiently many derivatives bounded. Okay, so there's some smoothness assumption. Okay. Now, so so this is also an exercise if you want to convince yourself that if alpha is between 0 and 1, this definition is equivalent to the usual definition of the Hölder spaces. For integer values of alpha, it's not equivalent. Okay, so for alpha equal 1, this definition here is not equivalent to C1, and for alpha equals 0, for example, it does not give you a continuous function. For example, the function log x would be in C0 with this definition, and of course log x is not a continuous function. Okay, so it gives you slightly larger spaces for integer values of alpha, but for non-integer values of alpha, it just gives you the normal definition of Hölder spaces. And this definition now has the advantage that, you know, it's a perfectly sensible definition also for negative values of alpha, right? So here there's nowhere in this definition where this needs to be a function. Okay, this could very well be a distribution. It's just that if this quantity is finite for some positive alpha, then this distribution has to actually be a function. But then you can choose alpha negative, and then the distribution is allowed to be an actual distribution. And this definition still makes perfect sense. And this condition here becomes simply empty because there are no polynomials of negative degree, and so this is always satisfied for every test function because it's just an empty condition. Okay? So now, with this definition, it's quite easy. So the first thing I want to check is what kind of space the noise here belongs to. Or maybe before that, okay, so maybe before that I should mention one very nice property of this definition is the following. It's that you have a very clean statement which tells you how much regularity you gain when you convolve an element in such a space with a kernel that has a singularity at the origin. Okay, so take a function k, say from, again, rd plus 1 to r, which is smooth everywhere except at the origin. Okay, so then we say that So definition, k is of order, say, beta positive, if when you take any derivative of k and you look at it at some point, space-time point z, then what you get is bounded by z to the power beta minus d minus 2 minus the degree, if you want, the degree of the multi-index in which you take the derivative, again counting the time component double, always as usual. Okay, so this is basically just a kernel that behaves like the function z to the power beta minus 2 minus 2, and so that when you differentiate it, the derivatives behave in the way that they should behave, right? So if every time you differentiate, it becomes a bit more singular. So for example, simply if you take any function which is smooth in the angular variable and is actually homogeneous under that scaling over there, would automatically satisfy a bound like this for some exponent, which is just the homogeneity of the function. Okay? And so now if you take a kernel like this, say compactly supported, so I don't want to have problems at infinity, then you can always convolve it with a distribution. Okay, so the convolution of basically the convolution of two distributions is always well defined if they don't behave too badly at infinity, or if at least one of them. So for example, if one of them is compactly supported, then the convolution of two distributions is always a well-defined operation. So I can take the convolution of a kernel like this with an element in C alpha, and so there's a theorem. So this is really quite a general form of Schauder's estimate, which is that if you take k of order beta positive and compactly supported, and you take zeta in C alpha for any alpha in R, okay, can be as positive or as negative as you want, then k convolved with zeta belongs to C alpha plus beta. Okay, so you get, that's why I defined it in a slightly funny way here, is so that here you just get plus beta. Okay? And that's also why the definition I just gave you of the C alpha spaces is a nice definition, because this is true whether this thing is an integer or not. Whereas in the usual formulation of Schauder estimates, you always have to make exceptions for integers. Whereas if you define the spaces in this way, then it's really true for integers as well. Okay, otherwise it wouldn't be true. So if you take the usual definition of Hölder spaces, then when this guy hits an integer, then the statement would actually be false. Okay, so why am I telling you this? Well, because when you want to solve the stochastic heat equation, okay, so the stochastic heat equation is a linear equation with an inhomogeneous term, and then you solve it by variation of constants. So it's just given by the heat kernel convolved with the right-hand side. Okay? The right-hand side being the space-time white noise. And so if you want to know how regular the solution is, all you have to know is first how regular space-time white noise is, and then what's the order here of the heat kernel. Okay? So now the order of the heat kernel is quite easy to figure out. Right? So if you look at the heat kernel, well, what does it look like? It's 1 over t to the d over 2, e to the minus x squared over t, modulo constants. And so what you see is first that this is a function which is indeed, it's smooth everywhere except that tx equals 0. Okay. Well, so I have to define it for negative t. I just set it to be 0 for negative t. Okay, so for positive t, it's equal to this. For negative t, I set it equal to 0. And then it is actually smooth if you take any non-zero value of x, it is smooth as you cross from positive to negative t, right? Because here you think you have a problem because this blows up, but this of course goes to 0 so fast that it kills, you know, any sort of algebraic singularity. So this is really smooth everywhere except that t equals 0 and x equals 0. There's really just one point where it's smooth, non-smooth, not the whole line. Okay, so it's smooth everywhere. And you see that it is homogeneous under the scaling up there. Okay, so if I multiply t by lambda square and x by lambda, then this exponent doesn't change at all. Okay? The only thing that changes is this term here. And so it has it's precisely of this form here, with this exponent here being equal to minus d over 2. Minus d, because t gets multiplied by lambda square. Okay, so if I multiply t by lambda square, this whole thing gets multiplied by lambda to the minus d. Okay, so this kernel is precisely of this form, with this whole exponent being equal to minus d. Okay? And so if this exponent is minus d, that means that beta is equal to 2. Okay, so this is of order beta equal to 2. Okay, because it's exactly homogeneous. And so it satisfies these bounds automatically. And so by Schauder's estimate, if we convolve anything with the heat kernel, we exactly gain 2 degrees of regularity. Okay, so that's the usual somehow gain of regularity for the heat equation. And so now, provided that we know in which of these C alpha spaces the space-time white noise lies, then we also know how regular the solution to the stochastic heat equation is. Right? So let's see. White noise. Well, we have to figure out how large this quantity is. And well, if we just take the definition that I gave you at the very beginning of the space-time white noise, well, we know that this is a Gaussian random variable, and we know what's its variance. Its variance is just the L2 norm, the square of the L2 norm of this object, right? Because it's just the L2 scalar product of this function with itself. So we know that the expectation of psi z lambda square is equal to simply the L2 norm of phi z lambda square. Okay. But now how big is the L2 norm of phi z lambda square? Well, phi z lambda, it was scaled in such a way that the integral doesn't change. Okay, so the integral of phi z lambda is basically 1. And so now how big is the integral of phi z lambda square? Well, it's, you take a function which integrates to 1, and you multiply it by a function which is bounded by lambda to the minus d minus 2. And so the integral is going to be bounded by lambda to the minus d minus 2. So this is certainly bounded by lambda to the minus d minus 2. And as a matter of fact, this is true in both directions. I mean, you can just check that by scaling, this is actually equal to lambda to the minus d minus 2 times the L2 norm of phi itself squared. Okay. And so what does this suggest? Well, it suggests that space-time white noise belongs to C alpha. Well, it somehow would suggest that it belongs to C alpha for alpha equal to minus d minus 2 over 2. Right? That's somehow what it suggests. But that's not quite true, because in the definition of C alpha, So here you want uniformity in phi. But so, you know, if you wanted, for example, to bound the expectation of the C alpha norm, you would have to have a supremum of all test functions that goes under the expectation, right? So you want this simultaneously to hold for all test functions. And here we just showed that for any given test function, it's of that order, right? So now there are lots of test functions. So you might think that, well, with so many test functions around, it might be sort of hopeless to actually bound this uniformly over all test functions. But it turns out you can do that. So it somehow works in a similar, you know, you have a similar problem when you want to figure out what's the regularity of Brownian motion, right? You compute expectation bt minus bs square, you get t minus s, and then you would conclude from this that it should be Hilda half. And of course we know that it's not, because we know that there's a log correction in the modulus of continuity. And it's exactly the same story here. Okay, so it turns out that somehow putting the supremum under the expectation is not as badly, it's not that badly behaved. You basically just lose a log. And so it's exactly the same thing here. You end up being in C alpha, but only for every alpha strictly less than minus C minus 2 over 2. Okay. And well, so now if we go back to the stochastic heat equation, so remember that was just dTu equal Laplacian u plus space-time white noise. Well, we can solve this by variation of constants formula. So let me be a little bit sloppy regarding somehow initial conditions and, you know, domains and things like this. So if we're a little bit sloppy about that, then we can just write u as heat kernel convolved with psi, where this convolution here is a space-time convolution. It's not just convolution in space. It's really a convolution in space-time. And well, we've just seen that the heat kernel is of order 2. And so what we conclude from this, if we combine it with which is saw above, is that u belongs to C alpha for every alpha less than, well, you improve by 2. So here you had minus d over 2 minus 1, and so the minus 1 just becomes a plus 1. So you have a 1 minus d over 2. Okay? So we see that in dimension 1, indeed, we recover a half. Right? And that's the thing that we had already guessed. Okay? So in dimension 1, this gives you a half. And so that was the argument we saw earlier, which is that in dimension 1, the stochastic heat equation locally for fixed time should actually look like a Brownian motion in X. And therefore, it should be of regularity Hilda half. And it also tells you, and since this is a space-time statement, it tells you that if you look at a fixed point in space and you look at the regularity of the stochastic heat equation in time, then it's Hilda a quarter in the usual sense. Right? And this is also sharp because you can actually prove, well, you can completely characterize that process. And if you look at the solution to a stochastic heat equation at a fixed point in space as a function of time, it turns out that it actually is basically a fractional Brownian motion with Hurst parameter 1/4. And so that's perfectly in agreement with what we've obtained here. Now the other thing you see is that as soon as d is equal to 2, this alpha becomes negative. Right? So in dimension 2, this is already 0. So it tells us that in dimension 2, the solution to the stochastic heat equation is in every C alpha for negative alpha, but it's not in C0. And so in particular, already in dimension 2, the solution to the stochastic heat equation is itself not a function. It's not a function-valued solution, but it's still a distribution-valued solution. And that's, again, it shouldn't surprise us because in one dimension, we saw that locally, the solution to a stochastic heat equation looks like a Brownian motion. And the analog of the Brownian motion in 2 dimensions would be the free field. And indeed, the solution to the stochastic heat equation in any dimension just looks like the free field locally. And the free field, we know that in dimension 2, it's already not a random function, but a random distribution. okay, which has in some sense some kind of logarithmic blow up at every point, and that logarithmic blow up is somehow the logarithm that we lose when we put the supremum under the expectation in a way. Okay. Okay. So now, let's go back to these equations. Right. So we've just seen that here in dimension 1, the solution to the linear part of the equation, so to the stochastic heat equation, locally looks like a Brownian motion, so it has regularity 1/2 in space. And so if you take its derivative here, this actually looks, at every instant of time, looks like a white noise in space. Right? It looks like the derivative of a Brownian motion in space. And so obviously I'm not allowed to square it. Right? So there's clearly a problem here in what this equation means, because you have to square here something that looks like white noise, and you're not allowed to square white noise. And well, here in dimension 1, it's not a problem. I can take the cube of something that looks like a Brownian motion. But then in dimensions, so here I claimed that it would work up to dimension 4. And so in dimension 2 and 3, you clearly start to have a problem. Right? So in dimension 2, it's just borderline, so it might not be so much of a problem to take the cube of something that looks like a free field in dimension 2. But you see in dimension 3, it starts to become really kind of quite tricky to figure out what the meaning of this term here is. Right? It's the same for all of them, right? So here, well, okay, so here you have just white noise in space. We haven't encountered that one yet, but it turns out that white noise in space, you can do exactly the same argument as before. And that actually belongs to C alpha for every alpha less than just minus dimension over 2, minus space dimension over 2. And then, so the solution to this equation, you would expect it to be in C alpha for alpha less than 2, minus dimension over 2 by a Schauder estimate. And then you have the problem of multiplying a function of regularity 2 minus dimension over 2. Well, it's a function at least up to dimension 4 here, right? With a distribution of regularity minus dimension over 2. Okay? And, well, there's a theorem that tells you that you can, if you have a function in some C alpha space and a distribution in a C alpha space with a negative, say in a C beta space with negative beta, and you want to multiply the two, then the product is well defined if and only if alpha plus beta is positive. Okay, so this product here is well defined if and only if 2 minus d over 2 minus d over 2 is positive. So that means if 2 minus d is positive, meaning that d is strictly less than 2, which again is basically just d equal 1. Right? And so if you want to define this equation here in dimensions, so again, I claim it actually works up to dimension 3, and again 4 is the dimension where things break down here, then it's not clear what the product here means. And well, this one basically all hell breaks loose because, well, this product is ill-defined, but then this product is ill-defined as well, and this product is also ill-defined. So somehow none of the products here should be well-defined. Okay? And so the question is, well, what sense can you give to these equations? So in some cases there might be tricks. So in the case of the KPZ equation, there's a very special trick that works very specially for the KPZ equation. But is there a more general method that allows you to give a meaning to these equations? And then even, okay, so if you have a meaning to the equation, you would still want to know that this is somewhat stable, right? So you would want to know, okay, so if I somehow regularize it in a certain way, right? So a natural way of regularizing it is to replace these white noises by things that are almost white. So things that have correlation functions that look like a delta function but are actually smooth functions. So then there isn't any problem of products not being well posed because all of these things would actually be functions. And then you can ask yourself, you know, these objects that you define stable as you perform such a regularization and then remove the regularization. Okay? And the claim is that there is a perfectly stable way, sort of nice way of defining these objects. But then what you get, so it's clear that you cannot, right? So what should be the statement? Okay? So if you want to have some kind of convergence statement. So it's clear that if you just regularize this noise, so say I put a little epsilon here, which really just means that psi epsilon would be some kind of approximation to white noise, right? So for example, psi epsilon, well, one way of defining it is you take psi and you just convolve it with some phi epsilon where the integral phi is equal to 1. Okay, so you just take some compactly supported test function that integrates to 1, you rescale it like a delta function so that it has scale epsilon, and you convolve your white noise with it. Then you get something which is perfectly smooth and which still looks like white noise on large scales, and it's just smooth at small scales. Now, of course, if you just look at this equation here, for fixed epsilon, it makes perfect sense. But now if you send epsilon to 0, obviously this term is going to blow up. And so the solution to this equation is certainly going to blow up as epsilon goes to 0. So I can certainly not expect to have a limiting theorem where I just say, oh, well, this converges to a limit, and then I define this limit to be the solution to the equation. Okay? And so here, the correct way of doing it is you have to simultaneously subtract a constant c epsilon, and then the claim is that if you choose this constant correctly, then this converges to a limit. And so now you'd say, well, you've actually changed the equation, right? So what does this mean? Well, here it turns out that you haven't really changed the equation, right? Because what's the effect of subtracting c epsilon? The solution to the equation with the c epsilon is exactly the same as the solution to the equation without the c epsilon, to which you simply subtracted c epsilon times t. Okay, so it's really just like when you get a central limit theorem, you have to somehow subtract the law of large numbers part, and then what's left might converges to a Gaussian or something, right? So this, you should think of this as being something a bit like a central limit theorem, okay, where this part would come from the law of large numbers. So if you go back to, I told you that you can get this equation as a limit of these kind of interface fluctuation models. Well, when you do this, then you take an interface fluctuation model which is asymmetric, so it has more of a chance of going in one direction rather than the other. So then it's going to have some average speed. And you have to subtract the average speed in order to actually see some fluctuations. And this term is basically the average speed that you subtract, right? Or it's actually the next order correction to the average speed, but still, it's essentially related to the average speed. Okay, so now here, there's a similar thing. So if you're in dimensions, if you're in dimension 1, there's no problem. Okay, but if you're in dimensions 2 and 3, then a priori the equation is ill-posed. And well, it turns out, so if you simply take this equation here and you send epsilon to 0, then the sequence of solutions does actually converge to a limit, but in a not very interesting way, in the sense that the limit is just 0. Okay? So that's really not what you want. You don't want to say simply, oh, the solution to this equation is just 0. That's not a very interesting object. The reason why this is the case is that the stochastic heat equation wants to look like a free field, which has somehow which looks very spiky. It has somehow quite large fluctuations at every point. But then this minus phi cubed term here sort of knocks down the fluctuations and makes them much smaller, but it doesn't really change the frequency, if you want, of the fluctuations. Okay, it just knocks them down. And so then if you take the limit, well, it just locally averages out and you don't see anything. Okay, so that's somehow intuitively why this converges to 0. So if you simply take a limit like this, it's not interesting. But it turns out that here, what you can do is you put a constant C epsilon here, and then it turns out that there is a joint limit. So if you choose this constant in the right way as epsilon goes to 0, then this has a limit. And again, the limit is sort of stable in the sense that it doesn't really matter how you regularize the noise here. You can even replace your white noise by something non-Gaussian as long as it converges to white noise, in a sufficiently nice sense, and it's stationary. Then the sequence of these solutions is going to converge to a limit, and the limit is always going to be the same. Okay? The way you have to choose these constants might depend on details of how you approximate your white noise. Okay? And here it's the same. Here it's a similar story. So if you want to get a limit, you cannot just look at this equation here. So here the equation that you have to look at, so yeah, first maybe I should, again, there's a physical interpretation to this constant here. So if you think of this as being approximated by something like an Ising model with sort of long-range interactions, which you have rescaled in the right way, then the interpretation of this constant here is essentially how far you are from the critical temperature. And the fact that it diverges, it just means that basically the mean field critical temperature is not a good approximation, is not a good enough approximation to the actual critical temperature of the system. And this sort of encodes the higher order corrections to this critical temperature. And so here it's the same thing. So you have to actually add a term like this. And then again, the claim is that in dimensions 2 and 3, if you do this, then there's a choice of these constants so that you get a limit. And again, the limit doesn't really depend on how you approximate things. And here the interpretation is that, well, this constant essentially does deconditioning of the particle being alive, right? Because what does this do? If you look at the solution to this equation and the solution to this equation, well, they're actually the same. Just one of them is multiplied by e to the c epsilon t. Right? So you can, if you take the solution to this equation and you multiply it by e to the c epsilon times t, then you just get the solution to this equation here. Okay? And so what it tells you is that, well, this term here, it's essentially a correction to the average rate at which your particles get killed. Right? So you have these particles in this random environment. The environment somehow kills the particles. There's going to be a leading order, which is simply the average value of the environment. And then this constant here encodes the higher order corrections to that leading order. Okay. And here the interesting thing is that in this equation you don't have to do anything. So here actually you can just approximate this, and whatever your manifold is, if you choose, okay, so here you have to choose the sigma in the right way. So you choose the sigmas in such a way that the covariant, that the sum over I of the covariant derivative of sigma I in the direction of itself is equal to 0. And that's very natural. It just says, for example, one way of doing this is you take your manifold, you embed it in a high enough Euclidean space. Okay, you can always do that. And then at every point, the way you choose your vector field sigma I is simply you take the ith coordinate vector in the ambient Euclidean space and you project it onto the tangent space. Right? So that's a very natural way of choosing the sigma i's in the first place. And if you choose them like this, well, first they do generate the metric in the right way, and then they automatically satisfy this condition here. And the claim is that if you choose the vector fields like that, then automatically here there are no divergences showing up. Okay, so if you simply regularize the noise, there is a limit as epsilon goes to 0. Here we don't we don't have a complete characterization of to how extent this limit is actually canonical. Okay, so here in principle you can get a family of limits with finitely many parameters that depend on sort of details of the noise, and somehow depending on what kind of additional structure you put on things, you can kind of reduce that family, but we haven't figured out a good way yet of reducing it to just one element. So we don't have somehow one absolutely canonical object. But for example, as soon as your manifold has some symmetries, then it becomes completely canonical. So if your manifold is actually a symmetric space, something like a sphere or so, then this converges to a limit, and the limit is really canonical in the sense that, you know, any regularization gives you the same limit. Okay. If the manifold is not symmetric, then you could get different limits, but they don't. You have some sort of characterization of by how much they differ or to what extent they actually differ from each other. Okay. So So in the last 10-15 minutes, let me actually look at the simplest non-trivial example here, which would be this one in dimension 2, and show you how in that particular case you can give a meaning to this equation. Okay, and so that's due to the Prato in the Bush. I don't know, around 2000, I don't remember, 1, 2, something like this. And so that's 5, 4 in dimension 2. And so to be precise, let me not worry about what happens at large scales. So I put this on a 2-dimensional torus. And so the idea here is the following. So I want to encode the fact that locally the solution to this equation is actually essentially a perturbation of the linear equation, of the stochastic heat equation. Okay. And so one way of encoding this is to simply say, well, I look for solutions that are of the form solution to stochastic heat equation plus some remainder. And then with a bit of luck, the remainder is better behaved, and so maybe I can do something with this. Okay? So I'm going to look for solutions of the form phi equal to u plus, say, v, where, well, u is just the solution to the stochastic heat equation. Okay, and v is just a remainder term. Okay, so in that case, what do you get? What do you get for v? Well, if you simply plug this into this equation, you write down the 1 for phi, you write down the 1 for u, you subtract both equations, the xi's cancel out. The only thing that's left is this term here. So let me write this as dtv equal to Laplacian v. So let me work at fixed value of epsilon. Okay. So then I have my c epsilon times phi, but phi is u plus v. And then I have a minus u plus v cubed. Okay? And so now what I'm going to do is I'm going to regroup these terms somehow in the right way. And you're going to see in a moment why I'm going to regroup them in this way. So how do I want to regroup these? So I want to expand the cube here. Okay, so the cube here, I want to write it as minus u cube minus 3u square v minus 3 uv square minus v cube. Okay. And then I would like to combine the c epsilon v term here with the minus v cube term. So right here, so let me put this on the next slide. Okay, so that's the first term. So I've used up this one and this one. And then I have a term with the v square, so I write this as minus 3u times v square minus c epsilon over 3. Right, so now this term here is exactly this term here, and this term is exactly this term here, right? Because the 3's cancel out. And then I just keep the remaining terms, minus u cubed minus 3 u square v. Okay. And now the claim is that if you look at this term and this term here, if you choose the constant c epsilon in the right way, then these two terms actually converge to nice limits. And why is that the case? Because I can choose. So first, I see that this is exactly the third Hermite polynomial. Okay. So remember, the third Hermite polynomial is, well, x cubed minus 3 times x. So this is the third Hermite polynomial at v with constant c epsilon over 3. And this is the second Hermite polynomial at v with constant c epsilon over 3. So in both cases, this is of the form some Hermite polynomial of v with a constant that I'm still allowed to choose, but it's the same constant in both cases. And so in these cases, it's c epsilon over 3. Yeah? And so if I choose, so now I choose c epsilon over 3 to be the expectation of v square. Okay, so this oh, sorry, I messed up. Oh, I mixed up u's and v's. Oh, I'm sorry. Okay, so this is all completely symmetric in u and v, okay? But I really wanted to do this grouping with u's instead of v's. So let me, I think at this stage it's probably easier if I do it like this. Okay, okay, so now the v is just the solution to the stochastic heat equation and u is the remainder. Okay? So v is just some Gaussian process, right? So if I take here my mollifier convolved with white noise, this is a Gaussian process. This is a linear equation. What I get is a Gaussian process. I make it stationary. Okay, so I look at the stationary solution of this. So I have a stationary Gaussian process. So its variance is the same at every point. And so I don't need to specify where I choose it. I just choose it somewhere, say at 0. But it's the process which is chosen so that it's stationary. And so it's the same everywhere. And now this is going to blow up as epsilon goes to 0. Right? Because you can actually, there's a formula for it. You can do an explicit calculation which tells you what this is. It's going to be something like the L2 norm of the heat kernel convolved with your mollifier. And if you just do the power counting, look at how it behaves, you see that this actually behaves like log epsilon. It behaves like some multiple of log epsilon. Okay, so this blows up as epsilon goes to 0. So you choose the constant in a way which blows up in the right way as epsilon goes to 0. But if I choose this way, well, first you see that this choice makes the expectation of this term to be 0. Okay, so at least the expectation of this term doesn't blow up. And because here is, you see the third Hermite polynomial, it also makes the expectation of this term to be 0. Okay, so the same choice of the constant here makes the expectation of both of these terms to be 0. So at least they have a chance of converging to something. And it turns out that if you compute the variance of this term here, then one can do a calculation. What you see is you actually get so the variance of this term. So if if I call this term here, I don't know, say x2, and this term I call it x3 because it's some kind of third power of v. This is a kind of second power of v. If you look at the expectation, so first for v itself, so for v itself, there's a calculation one can do which tells you that the variance of v at a point z times v at a point z prime behaves again like a log of z minus z prime. Okay, so it's not surprising because it looks like a free field. It's sort of a time-dependent version of a free field. It turns out that in time it's also logarithmic. Okay, so this behaves like a log. And now, if you take something Gaussian and you take any Hermite polynomial of your Gaussian with parameter given by its variance, then it turns out that what you get for the covariance is simply the corresponding power of the original covariance. Okay, so that's a completely general fact about Hermite polynomials. And so expectation of x k, so here k is actually either 2 or 3 of a point xk z prime actually behaves just like log z minus z prime to the power k. Okay, so if you take these Wick powers of your process, and Wick power just means take the corresponding, the k, so kth Wick power means take the kth Hermite polynomial with parameter variance of your process. Then the correlation function for your kth Wick power is just the kth power of the original correlation function. Okay? But now you see this is something which is perfectly nice and integrable, right? So for every value of k, this is a nice integrable function. And so there is actually a limiting object. So here, of course, there are sort of epsilon regularizations of this, but that then as epsilon goes to 0, they converge to just some power of a log. And so this tells you that these objects, these xk's, converge. So xk epsilon, they converge to a limit xk as epsilon goes to 0. And the limit has its covariance. Is an object with this kind of covariance. The limit is, of course, not Gaussian. Okay, so one has to be a bit careful. But in some kind of L2 sense, it's quite easy from this to get that the limit, that these objects converge to a limit. And they actually converge, well, basically because of this log, they converge in C alpha for every alpha less than 0. Okay, so again, you can do some kind of Kolmogorov type criteria, which tells you that this blow up here is better than any kind of algebraic blow-up. It's just a logarithmic blow-up. So actually it belongs to all of these C alpha spaces. And so now you see, so for U, now you get an equation where I have here something which is in some C alpha space, but for alpha negative, but just slightly negative. And the same here, this guy is in some C alpha space for some slightly negative alpha. Same for that one, that was just the free field that I started from. And so now how do we expect the solution to behave? So now the solution to this equation, we expect it by Schauder again to be in C2 minus alpha. But alpha is just slightly negative, so C2 minus alpha is just slightly worse than 2. Okay? And so now these products, so here you still had products, and here you had products that might be ill-defined. They are perfectly well posed. So the U is an actual continuous function. It's in C alpha for almost alpha equal 2. And so, you know, this problem of multiplying, so here you can, it's no problem to multiply this distribution with this function, because this is in some C alpha for just slightly negative alpha. This one is for alpha almost 2, so the sum of the two exponents is very positive. It's almost 2. Right? So I told you that the criteria was that the sum of the exponents had to be positive. Here it's almost 2, so there's absolutely no problem in defining that product. And the same for this product here. And of course the cube here is not a problem because it's a continuous function. And so now this equation here is perfectly well posed. Right? And you can solve it by some fixed point problems. Okay, and you know, you can show this procedure, since this convergence here does take place in this C alpha space. Well, the solution here depends in a very stable way on these elements. So it depends continuously on these elements here, continuously in C alpha. And that tells you that somehow, you know, whichever way you regularized your noise to start with, as soon as you can show that these objects here don't depend on your regularization, then the solution to the equation is not going to depend on the regularization either. Okay. So in this particular case, so you saw the trick here. So the trick here was just to say, oh, I make the guess that my solution looks like the solution to the linear equation plus a remainder. Then I rewrite the solution in the right way in order to combine terms that are going to cancel each other out. I choose the constant in a smart way, in such a way that these terms that I've sort of extracted do converge to limits. And then I show that the equation for the remainder is well posed. And so you get your convergence result. Okay, and the choice here of C epsilon had to be the correct multiple of log epsilon here. Okay, and so what we're going to see tomorrow is somehow, you know, how do you play similar games in situations where this simple trick doesn't work anymore. Okay, so this simple trick here, it basically in all these examples, it works in this case in dimension 2 and in this case in dimension 2. And in all the other cases, this simple trick doesn't work. But we'll see that there is, in some sense, you can build a theory which in a way is some kind of generalization of this trick. Okay? And so that's what I'm going to talk about tomorrow. Okay, thanks. Yeah.
So this is a nice story about well-posedness of a question. But how well all this is prepared to study the dynamics? So you everywhere has time. Yes. So how it really evolves.
Right. Yes. So you can show. So now. So for example, we have a result now for this. So in this case here, the torus, we can actually show now that the dynamic really converges to equilibrium. So it's so there is a natural invariant measure for this process here, and you can show that you converge exponentially fast to that invariant measure. So you can show these kind of things. So in some sense, the object that you build is a Markov process which is actually quite well behaved. Okay, so it has somehow nice properties. So it has, for example, the Strong-Feller property. And so it converges to equilibrium relatively fast and things like that. So you can prove these sort of things.